Welcome back. So today we're going to look at transformations and we're going to break it into three sections. So our focus with transformations, and transformations really means how we distort or rearrange, functions or graphs depending on three basic characteristics. The first characteristic is what we'll call a dilation. So that's stretching the graph, either making it taller or making it wider. We can reflect the graph. Okay, so we can reflect the graph in the x-axis or we can reflect it in the y-axis. And then we can translate the graph. We can move it to the left or to the right, and we can move it up and down. So we call translating the graph, we call translations. And that's something for us to think about. So the first thing we're going to focus on, though, is dilations, and we're going to specifically talk about vertical dilations. Now, when we talk about vertical dilations, what we're talking about is dilating by a factor of a from the x-axis or along the y-axis. Essentially, what we're doing is, if we can look at this grey circle in the middle here, okay, what we're doing is we're stretching the graph along the x-axis. So we're making the graph taller in a sense. And that is expressed by, moving the graph either further upwards or downwards. But essentially what we're doing is we're stretching it away from the x-axis, or we're stretching it along the x-axis. Along the y-axis. Now, the general form that we use for this, so the general form, what we will say is fx, the original function, is being transformed to become a times fx. Now, when we consider this in our coordinates, we're going to start with just our basic coordinates, x and y, as they are. And we're going to then, with x and y, we're stretching it along the y-axis. Okay, so we're not doing anything horizontally to the graph, but we are multiplying every y coordinate by a factor of a. Okay, and we can express this as, okay, so we're not doing as an image. So x image, we're not doing anything to the image of x. We're not transforming anything to do with x. However, we are transforming the image of y. So I'm going to write y image equals ay. Now, if I put that in terms of y, that is written as y image on a. And then if I consider my function y equals fx, I'm going to substitute my images. So y image on a, because this y equals y on a, which I'm substituting here. And this is given as fx image. And this becomes y image equals a times fx image. And this means that our transform formed is just simply y times fx, which corresponds, so this corresponds with our general form. Okay. So our next part is when we're considering a horizontal dilation, and this is stretching the graph out along the x-axis, essentially making it wider. The language that we use here is dilated by a factor of a from the y-axis. Alternatively, you could get questions that says dilated by a factor of a along the x-axis. But our general form for this type of transformation is written as our original function fx becomes fx on a. So if we go back to our coordinates, essentially what we're saying is we start with x and y, and we're multiplying our x coordinates by a factor of a, but we're essentially also not doing anything to our y coordinates. So what we can say here is our x image is becoming ax, and I could write that in terms of x as x image on A. And like I said before, we're not doing anything with our y coordinates, so just y image equals y. If we then consider y equals fx, and we do some substitution here, y image f x image on A, and this becomes an expression, or transformed expression, of y equals x on A. And this, if you note, is the same as this expression. Okay? Especially this section. Okay? So that's how the general form of these dilations are coming about. But you must read the language. You must be careful to, or must be sure to distinguish whether you're dilating it vertically or horizontally, and it is all in the language. Okay, so let's have a look at a problem. So determine the rule of the image when the graph of y equals x to the 3 is dilated by a factor of 2. The first part is asking us to dilate it from the x-axis, and the second part is asking us to dilate it from the y-axis. So for part A, I'm concerned as dilating it from the x-axis. From the x-axis means that it's going to be a vertical dilation. So therefore, my y image is being distorted by a factor of 2 times y, and therefore I can write y as equaling y image on 2. Therefore, if I use my original expression, y equals x cubed, I'm going to use some substitution here. Y image on 2 equals x image or cubed. Y image, I'm going to put the expression in respect to y image, and that's just 2 x image cubed, and therefore my expression can be written as 2x cubed, and this is my transformed expression. Section B says that it's been dilated by a factor of 2 from the y-axis. So this means that it's going to be a horizontal dilation, and I can say that x image is 2 times x. Therefore, x by itself can equal x image on 2. Therefore, I'm going to use my original equation, y equals x cubed, and I'm going to start putting some substitution in. Y image equals x image on 2, or cubed. Y image equals x image on cubed, and I can see here that I'm going to say 2 to the cubed is 8, and therefore my expression, transformed expression, is x cubed on 8. That's my answer. Okay, so considering another question, determine the factor of dilation when the graph of y equals square root of 5x is obtained by dilating the graph of y equals the square root of x. And it has two parts. Firstly, it's saying from the y-axis. Okay, so from the y-axis, that's going to be a horizontal dilation. And B, from the x-axis, that's going to be a vertical dilation. So let's start working through question A. So I know that this is going to be a horizontal dilation, so I'm going to say x image equals ax, and therefore x equals x image on A. Therefore, y image equals the square root of x image on A. That's taken from the transformed form of it being dilated. Okay, therefore, if y equals the square root of 5x, and this is going to equal the square root of x on A, I can just focus on 5x equaling the square root of x on A. This becomes 5x equals x on A. We have a cancellation here of the x's. There I have 5 equals 1 on A, and A will equal 1/5. So what this essentially means is there's a dilation by a factor of 1/5, okay, from the y-axis. If I look at B, okay, so looking at B, it says from the x-axis, that means that it's going to be a vertical dilation, and I can use y image equals AY, okay, y then equals y image on A, and this becomes, if I substitute this in, y image on A is going to equal square root of 5x image, and y image is going to equal A. Sorry, that shouldn't be 5x. Let me correct that. AX image, okay, and this is going to equal also square root of 5x. So essentially what I'm saying is A square root of x equals the square root of 5x. A equals square root of x. I can separate my values inside my square root value to have that. There's a cancellation here, and therefore A equals square root of 5. And this means that I have a dilation by a factor of 5 from the x-axis. Okay. So now considering reflection. So we have two types of reflections. Okay, we have reflection in the x-axis and we have reflection in the y-axis. When I talk about a reflection in the x-axis, I like to refer to this as a vertical reflection. The reason why I call it a vertical reflection is because essentially what we're doing is we're flipping the graph upside down or flipping it vertically. What we discuss here when we're doing this in the general form, okay, so our general form for this is fx, our original function, is becoming negative fx. And our coordinates x and y are becoming, there's nothing happening to x, but our y coordinate is being flipped upside down, therefore it becomes a negative. And we have y image becoming negative y. This can be then written as y equals negative y image. And then if I discuss y equals fx, negative y image equals fx image, okay, y image equals negative fx image, and this transform form is written as negative fx, y equals negative fx. This form, this general form here, is the same as what we're working with at the top. The other type of reflection that we can discuss is reflection in the y-axis. I like to refer this to as a horizontal reflection. The reason why I call it a horizontal reflection is because we're flipping our coordinates horizontally. So we're flipping our x coordinates. The general form for our horizontal reflection is fx. Our original function is becoming f negative x. If we talk in terms of our coordinates, basic coordinates x, y, we're not doing anything to y, but we are changing or putting the negative value of x to the x coordinate, so negative xy, and therefore x image equals negative x, and I can write that in terms of x. That's negative x image. Therefore, if y equals fx, I can start substituting in. Y image equals f negative x image, and we can write this as our transformed form y negative x. Okay, so having a look at some problems. So the first problem that we're looking with the reflections, or problem 3, find the equation of the image when the graph equals x minus 1 squared and is reflected in the x-axis, that's part A, and then part B in the y-axis. So let's focus on part A. Reflected in the x-axis, that means that that's a vertical reflection, okay? We're flipping the graph upside down vertically. So I'm saying that y image equals negative y, okay, or y here equals negative y image. Therefore, if I start with my original equation, y equals x minus 1 all squared, and what I'm going to do here is I'm going to substitute my values in. Negative y image, x image minus 1 all squared, y image by itself, let's isolate it by itself, negative x image minus 1 all squared. I can now write this in my transform form, x minus 1 all squared. Okay, and if I look at this graphically, this will be my answer for what my expression should be. But if I think about this graphically, my first graph here would have been a parabola looking like so, okay, and it would have a turning point intercept at x equals 1, or we might call it 1, 0. If I consider this function here, that still has a turning point at 1, 0, but it's a negative parabola. So we can see here that it is effectively a reflection of the original graph. If we then look at question B, okay, so this is a reflection in the y-axis. So this is going to be a horizontal reflection, and x image is going to equal negative x. If I write that in terms of x, that's negative x image. Therefore, if I work with my original equation, I'm going to get y image equals negative x image minus 1 all squared. Now, I am going to consider this expression, and there's a tricky part that I can do with this with the factorization. So I'm still going to keep it as y image and x image, but what I'm going to do is I'm going to take a factor of negative 1 out. I'm going to multiply that by x plus 1, and all of that is going to be squared. I can't take that negative 1 outside the bracket because it is tied to the power of 2, or the square power. And what I can say here is y image equals negative 1 squared, which is just positive 1. So that leaves me with x image plus 1 all squared and y equals x plus 1 all squared, and this is going to be my answer. Again, if I consider my graph, what's happening graphically here, okay, we've got the parabola coming through, okay, 1, 0 as my point. But if I consider this expression, and I consider where the turning point is going to be, that turning point in x-intercept will be at negative 1, 0. It's still a positive parabola, so it is going to go up likewise. And as we can see, there's a reflection. So there's a definite reflection here in the y-axis, where in the last question, or part A, there was a definite reflection in the x-axis. Okay, so the next problem is state the transformation which maps the graph of y equals x to the graph of y equals the square root of negative x. Essentially what we're saying is square root of x is leading to the square root of negative x. We can effectively get rid of the square root signs and just say that that's x going to negative x. That's basically a horizontal reflection. So we can say here, reflection in the y-axis. And we can consider this graphically. So if I consider, okay, the initial graph of y equals x, that's what that will look like. Okay, if I consider the graph of negative x, that graph will definitely look like that. And we can say that there is a reflection along the y-axis as such. Okay, so now talking about horizontal translations. Okay, so horizontal translations can be stated, moving the graph or moving the function to the right or to the left. Okay, they will use in the positive direction of the x-axis. That means moving the graph to the right. If they say moving the graph in the negative direction of the x-axis, that means that you're going to move the function to the left. In general, the rule that you apply with a horizontal dilation is our original function fx becomes fx minus c, okay? And that means that we're translating it c units to the right. In our coordinate form, xy is becoming x plus c y, and what it means, the x plus c, is effectively we're moving the graph, or in terms of x, okay, horizontally, plus c units. We can say from our image point of view that x image is going to equal x plus c, and therefore we can write x in terms of x image minus c. And therefore, if I have y equals fx, y image equals f x image minus c, okay, and this can be written as y equals f x minus c. Now, this expression is exactly the same as the general expression which we apply to such translations. The next form of translation that we can look at is when we're dealing with a vertical translation. So that means moving the function either up or down. They may use the language positive direction of the y-axis or negative direction in the x-axis. The general form that you would use here is the original function fx becomes fx plus d, and therefore you'd have x and y become x y plus d. And as you can see, we're only really changing what happens in the y coordinate. So our y image equals y plus d, okay? And if I wrote that in terms of y, that's y image minus d. Now, therefore, if I deal with y equals fx, okay, and substituting, y minus d equals fx image, and y image by itself equals fx image plus d, and we say y equals fx plus d in our transformed form, and this expression is the same as our general expression about that. Okay, so let's have a look at some questions. So find the equation for the image of the curve of fx, where fx is 1 on x, under these following translations. So we're going to say here that we have, start with our coordinates, x, y, and then we're going to say translation of 2 units in the positive direction of the x-axis. So that's x plus 2, and 3 units in the negative direction of the y-axis, y minus 3. Therefore, x image equals x plus 2, and we can write x as equaling x image minus 2, and y image equals y minus 3, and we can write y as y image plus 3. Therefore, if we use our original equation of y equals 1 on x, what we can say here is y image plus 3 equals 1 x image minus 2, and y image equals 1 x image minus 2 minus 3, and therefore our expression can be written as y equals 1 x minus 2 minus 3. We might want to write it in terms of fx as it was stated in terms of fx. And that's our answer for that question. All right, so last question here. Okay, it says, state the transformation which maps the graph of y equals fx to the graph of f1. Okay, in our first part, we're saying here that I'm going to have a look at this x minus 2 squared, and I'm going to map the x together. So what I'm saying here is x image minus 2 is going to equal x, and that means that x image equals x plus 2, and that means that there's a translation here of 2 units to the right or in the positive direction of the x-axis. And also I'm going to say y image equals y plus 3. Therefore, this means that it's translated 3 units upwards. Okay, and the second part here, I'm going to again focus on my x. So my x image plus 2 equals x. X by itself becomes x image minus 2, or apologies, let's take that back. The x image becomes x minus 2. This means that it's translated 2 units to the left, and we can say here that our y image equals y minus 3. This means that it's translated 3 units downwards. Okay, so we're going to leave that there for today. Keep on working at it, and if you have any problems, please let me know.